One important fact at the beginning of chapter 3 is called the linearity of the derivative operator. Linearity of the derivative operator. This linearity of the derivative operator, I have mentioned before, actually, and it can be stated in various ways. The simplest way to think of it is in the case where you're trying to differentiate the sum of two functions. Say f of x plus g of x. And you're wondering, you got this function f of x plus g of x. You're wondering, what is its derivative with respect to x? What is d dx of f of x plus g of x? I'm using the d dx operator notation in front of it. I could alternatively use this entire thing with a prime there. That would be quicker. But I prefer using the d dx operator to say, I'm taking the derivative with respect to x of whatever's inside the parentheses. The derivative of a sum, this is the sum of two functions, can be proved to be the sum of their derivatives. And here I'll go to prime notation, f prime of x plus g prime of x. When you make certain assumptions, what assumptions do you need to make to be able to say this? You need to assume f and g are differentiable at whatever value of x you happen to be thinking about. I'm doing an arbitrary value of x here. I could imagine x is a specific number when I think about this, and it's still true. This is as long as f and g are differentiable at the value of x. Okay, probably best to imagine x to be some specific number, but it could be any number, and so I'm using a variable name. If what this is really saying, if I wrote it as a theorem, as this is, it's not really a theorem, because theorems should be written in sentences. They should be if-then statements. But if I did write it as a theorem, I'm not going to bother. It would say, if f and g are two functions that are differentiable at some value of x, then f of x plus g of x would also be differentiable at that value of x, and its derivative at that value of x would be the sum of these two derivatives. The derivative of f and the derivative of g, both evaluated at that number x. This property, this linearity property of derivatives, I hope it's somewhat intuitive. It would be something you would hope would be true. It is essential for the usefulness of calculus. If this were not true, calculus would be way harder than it is. Now, I know it's already hard enough as it is, but it would be way, way even harder, okay, if this were not true. This is part of what makes calculus useful. Why is it true? What's the essence of the proof? And do you have to do this proof on the test? No, you do not have to do this proof on the test. I'm going to do it in class. You'll also find it in the reading in the beginning of chapter 3. I think it's worthwhile to show you, to remind you, and this is part of reviewing for your exam, to remind you of, first of all, the definition of the derivative, and secondly, properties of limits, which you should know for exam 1. First, what's the definition of the derivative? It's the limit as h goes to 0 of a difference quotient. Right? This is something you should know for exam 1. What do we put in the top and the bottom of this fraction here? It's always been, if you have just one function f, it's always been f of x plus h minus f of x all divided by h. That's the definition of the derivative. Limit definition of the derivative. Limit of a difference quotient is what this thing is called. But we don't just have a plain f here. We have the sum of two functions. We have a new function. I could call this h of x if I wanted to, although using the letter h would be bad since I have an h there. Okay, j of x is f of x plus g of x. And I could write a j of x plus h minus j of x all divided by h. But j of x is the sum, so I might as well just write the sum. f of x plus h plus g of x plus h would be j of x plus h. Please make sure you shut the door more when you leave. Minus j of x. What is j of x? It's f of x plus g of x. All divided by h. Yeah, if I call this j of x, this is j of x plus h, and this is j of x. But it is a sum. I might as well just write it as a sum and not bother with the j. What do you do here? Abstract problem. I don't know what f and g are. They're arbitrary differentiable functions at x. Can I still prove this? I must have to relate it to these derivatives, right? Is that what you're about to say? I got to relate it to those somehow. Well, sometimes you just try the only thing that makes sense to try. Try simplifying. How can you simplify? How about distribute the minus sign through for one thing? So I'm really subtracting f of x and I'm really subtracting g of x. And if I want to relate it to the derivatives here, maybe I need to do a little rearranging, group the f's together and group the g's together. Maybe like this. And using parentheses for emphasis. That's true. I can definitely do that. I did a few, that's just algebra. I just did a few algebra steps there. I distributed the minus sign through, which is really distributing. If I had a plus -1 times this thing, it's really the same as distributing a -1 through. Because when you subtract something, it's the same as adding -1 times the thing. And then it's just rearranging with the commutative property for addition, really. Subtraction is adding a negative, and so it's okay to do that rearranging with the minus signs there, as long as I have them in the right spots. Okay, can I just say right away this equals f prime of x plus g prime of x? No, I should use a property of limits. I should also break this apart into two pieces. Two fractions, one of which is the difference quotient for f, and one of which is the difference quotient for g. Why is this step okay? That's also just algebra. Effectively, I'm reversing the process of adding fractions. Right? Think back to what would it be? 5th grade, when you add fractions, you know, what's 1/2 plus 1/3? You got to get a common denominator of 6 in this case. And then you add the numerators and keep the denominators as they are. Effectively, what I did here is I went backwards. I went from there to there. I mean, I could keep the, or I went from here to here, thinking of 5 as 3 plus 2. I went from here to there. I broke apart this fraction that already has a common denominator into the sum of two pieces. Now I can use a property of limits. The limit of a sum of two functions is the sum of the individual limits, assuming those individual limits exist. And they do, because I'm assuming f and g are differentiable at x. That is a property of limits that you'll find in chapter 1. And we, in fact, use this property back in chapter 1 for homework problems. Maybe not in this situation, but you used it in some problems. The limit of a sum of two things is the sum of the individual limits, assuming these limits exist, but they do exist because I'm assuming f and g are differentiable at x. That one equals f prime of x, this one equals g prime of x, done. Technically, what I've shown you here is not a proof, because as I've emphasized, proofs are arguments. They really should be written in sentences, as I showed you with the logarithm proof a couple weeks ago that you should be able to do on the exam, or maybe different log properties you should practice for the exam. Proofs technically should be written in sentences, not even like geometry, where you have like the statement and reason tables. That's not really a proof. I mean, yes, your geometry teacher said it was a proof, but to tell you the truth, it's not really a proof. It's just an outline of a proof. Good enough for many people, but proofs are arguments. It's like you're giving a speech and you're trying to explain step by step why something follows from something else using logic. And yes, you could argue that what I have here is logical, but I didn't write any sentences. Now, of course, people get all upset when you say write sentences because that's kind of a pain. And do I agree it's a pain? Well, yeah, especially if you're writing and you're feeling tired. You want to go to sleep. You want to do something else. I know the feeling, okay? I've been there, even though I like doing proofs, compared to most people, at least. Do I always require proofs? Well, no. A lot of times showing things like this are good enough. But besides not writing sentences here, why is this not a proof? Because I'm implicitly assuming all along in these calculations that f and g are differentiable at x. That I can do this step right there because I'm assuming really that these limits exist because f and g are differentiable. So because of that, that's another part of the reasons why this is not a full proof. But I think it's a good enough kind of thing that if I put this on exam 2, you should be able to do it. Will this show up on exam 2? Maybe. Maybe not the full proof, but maybe I'd give you steps and you'd have to give me reasons for them or something. Question?
So how would you go about making it so you're not assuming? How would you think about it?
You'd have to say things in the right way. It's a matter of putting things in the right order. You'd have to start by saying, hey, I know f and g are both differentiable at x because that's what I'm assuming. So this is equal to that and this is equal to that. These limits exist and they're equal to these things. And therefore, this limit of this sum equals this by a property of limits. And this limit equals that, and this limit equals that by some algebra. And hey, that's the definition of the derivative. So it really would be a backwards argument of what you see here to be a truly rigorous argument based on stating precisely what you are assuming. Okay.
So you can just state, we're assuming.
Yeah, yeah. I know I said that very fast, like in 10 or 15 seconds. I don't expect you to remember that. And I'm not testing you on exam 1, but you might want to remember for exam 2 that we did this before exam 1 and review it then. I'll probably review it again next week. But for the moment, it was just to reemphasize the importance of differentiability. If f and g are differentiable at x, then so is f plus g, and that derivative equals the sum of these two derivatives. It's to emphasize the importance of differentiability for the moment. And properties of limits to review that. And the definition of the derivative to review that.